All right, here's the first lesson for the logarithmic functions unit in the advanced functions course. This section, I'm just going to introduce you to what a logarithmic function is. And most importantly, you're going to learn by the end of this lesson how to rewrite exponential equations in logarithmic form, or vice versa. So let's get started. Before I teach you about logarithmic functions, I have to remind you about exponential functions, because it turns out those functions are inverses of each other, so they have very similar properties. We're going to be working a lot with exponential functions in this unit. So let me start by reminding you about what exponential functions look like. And here we go. Remember, exponential functions have the variable x in the exponent. That's what makes it an exponential function. And this is the general format of an exponential function, where a is the initial amount, b is the growth or decay factor, depending on whether its value is bigger than 1 or between 0 and 1. X is the number of times a is going to be multiplied by b, so it's the number of times a is increasing or decreasing. And y is the future amount. Now we can calculate x, the exponent, by doing the total time divided by the time it takes for one growth or decay period. And I think it'll be a good refresher for us to go back and do a grade 11 example about exponential functions, just so you really remember what all these parameters mean and how we use them in an equation. So here's the example. An insect colony has a current population of 50 insects. So remember, initial population we call A. Its population doubles once every 3 days. Well, the fact that it's doubling means this is an exponential growth question, and our growth factor is going to be 2. And it doubles once every 3 days. So 3 days, that's our growth period. That's how long it takes for the population to double once. And part A says, what is the population after 12 days? So I want the population after 12 days. So this is like my y value, and that's equal to the initial value times the growth factor, which in this case, because it's doubling every 3 days, our growth factor is 2. And how many times is it going to double in a 12-day period? Well, in 12 days, it's going to double 4 times. How do I know that? Because to calculate the exponent x that goes on an exponential function, we do the total time, 12, divided by the time of one growth or decay period, 3. So 12 divided by 3 gives me 4. Hopefully that makes sense to you, because if it doubles once every 3 days, in 12 days it will have doubled 4 times. And then we just evaluate this. P at 12 equals, so this 50 is doubling 4 times. Double once gets us to 100, double twice gets us to 200, double 3 times gets us to 400, double 4 times gets us to 800. So after 12 days, the insect population is going to be at 800. The important part of this question is part B. This is what I really want to focus on. It says, how long until the population reaches 25,600? So we want to set the population to 25,600 and figure out what amount of time is it going to take for that initial population of 50 to get there. Remember, that initial population of 50 is doubling every 3 days. That's how I set up this equation. Finishes at 25,600, starts at 50, and is doubling once every 3 days. And we want to figure out, well, what amount of time would have to pass so that I can get that initial amount to 25,600. Notice my unknown in this equation is in the exponent, which is what makes this a difficult equation to solve. And maybe in grade 11 you were shown different ways of solving this, but we want to transition to solving this using logarithmic functions in this course. So I'll take you through that in this example. So we would start by dividing both sides by 50, and we would get 512 equals 2 to the power of t over 3. And now we're trying to figure out what exponent goes on 2 to get 512. So maybe in your last course, maybe you just guessed and checked. Maybe it's 2 to the 5. Nope, that's too low of a value. Maybe it's 2 to the 11. Nope, that's too high of a value. And you keep guessing and checking until you figured out, oh, 9's the exponent that goes on 2 to get 512. So I need to make this t over 3 be equal to 9. So I need that t over 3 to be equal to 9, and that happens if t is 27. So you'd figure out that our answer to this question is 27 days. But I don't want you to have to be guessing and checking to find answers, and it's not always going to be a nice integer answer like it was for this one. So how are we going to do this algebraically? How do we figure out an exponent that goes on a power to get a certain value? How can I figure out what exponent goes on 2 to get 512? There's a function that does that for us. It's called a logarithmic function. I can evaluate log, and we say base 2 of 512. And what that does, that tells me the exponent that goes on 2 to get 512. And I know I want that exponent to be equal to t over 3. So that's how I would transition from an exponential equation to a logarithmic equation. In this logarithmic expression on the left side of the equation, this 2 is what we call the base of the logarithm, and this 512 is what we call the argument. And set up like this, log base 2 of 512, what that does, it evaluates what exponent goes on 2 to get 512. So let me just show you. If I were to do log base 2 of 512, I should get 9. Log base 2 of 512, this should be 9, because 2 to the power of 9 is 512. So if we evaluate log base 2 of 512, we get 9. And we know that exponent has to be equal to 9, and then solve that, we get 27. Now I briefly mentioned to you that a logarithmic function is the inverse of an exponential function. Let's look more in depth at that. So remember, the notation for inverse functions looks like this. So if you see f to the negative 1 of x, that doesn't mean the reciprocal of f at x, it means its inverse, something very different than reciprocal. And what do you remember about inverse functions? Inverse functions have their x and y coordinates reversed. So if f at a equals b, that means the inverse function at b equals a. More simply put with numbers, if on the original function you have the point 513, that means on the inverse function you would have the point 13,5. They just have all their x and y coordinates switched with each other. And if we look over here, I have the graph of a function and its inverse. Notice that those functions are symmetrical about this diagonal line y equals x. Let me remind you how to find the equation of an inverse function. Let me start by replacing f at x with y, because we know that's just function notation for y value. So y equals 3 times x minus 5 squared plus 1. I want to find the equation of the inverse of this function. Well, inverse functions have their x and y coordinates switched. So what do? We literally switch the x and y coordinates. X equals 3 y minus 5 squared plus 1. And then we just rearrange this to isolate y. So I would start by subtracting the 1 over. So x minus 1 equals 3 times y minus 5 squared. Then I would divide the 3. X minus 1 divided by 3 equals y minus 5 squared. And then I need to move the square over. The inverse of squaring is plus or minus square rooting. Don't forget that plus or minus. So plus or minus the square root of x minus 1 over 3 equals y minus 5. And last step, add the 5 to the other side. I'm going to put it in front of that term with the square root, but you can put it after. But typically you'll see it written in this format. So this is the equation of the inverse, 5 plus or minus the square root of x minus 1 over 3. And when we write the equation of the inverse, you should use the proper notation. Since the original function was called f at x, this is the notation for inverse, with that little exponent negative 1 looking thing, even though it's not really acting like an exponent. It's just notation that means inverse of a function. So here's our final equation. All right, now that you remember how to find the equation of an inverse, let's do that same process, but our original function isn't going to be a quadratic, it's going to be an exponential function. Oh, and before we do this example where we find the inverse of that exponential function, I put a little reminder of exponent rules for you here. These are going to be very important as we go through this unit. And you learned all these in grade 9. When multiplying powers to the same base, you keep the base, add the exponents. When dividing powers to the same base, you keep the base and subtract the exponents. When you have a power of a power, so an exponent on top of an exponent, you keep the base and you multiply those exponents. And if you have a negative exponent, that's equal to 1 over the power with the positive version of the exponent. And anything to the power of 0 is 1. I should note here, as long as x isn't 0, right? 0 to the 0 isn't 1, but any other value of x to the power of 0 is 1. Okay, let's go back to this example here. Find the equation of the inverse of this function. So remember, f at x just means y, so y equals 2 to the x is our original function. To find the inverse, we swap x and y, so x equals 2 to the y, and now I have to isolate y. One way to do this would be using a couple log rules that we actually don't quite know yet, but I'll use them anyway, and we'll talk more about them in the unit later. Hopefully in your last course you were introduced to something called the power rule of logarithms. Let me just take the log of both sides. So log of x equals log of 2 to the power of y. The power rule of logarithms tells us we're allowed to take the exponent of the argument of a log and write it as the coefficient of the log. So that means this would equal log of x equals y log of 2. And we want to isolate y, so I'll divide both sides by log of 2. So I would have log of x divided by log of 2 equals y. And then there's something called the change of base formula that I've written here. And I'll talk to you a lot more about this as we go through the unit, and I'll even show a proof of it to you later. But if we have two logs being divided, and those logs have the same base, now we don't see a base on those logs, it's actually 10, it's called the common logarithm. Once again, we'll talk about more of that later. But for now, just notice that if we have this format, we could rewrite it in this format, where this number becomes the base of the log, and this number becomes the argument of the log. So I could rewrite this as log base 2 of x. And there we go. This is our inverse function. So I could say my inverse function is equal to log base 2 of x. So the inverse of 2 to the x is log base 2 of x. So this is just showing you that log functions are inverses of exponential functions. Now, if you followed along with what I talked to you about in example 1b, maybe you would have been able to go right from here to here and skipped all those in-between steps. So if you remember what a logarithm means, it means what exponent goes on the base to get the argument. And we know that's equal to y. So that tells us that y is the exponent that goes on 2 to get x. Or another way of saying that, 2 to the y equals x. And that's exactly what we had here, 2 to the y equals x. So what's written there and what's written here mean the exact same thing, it's just written in two different ways. So we'll spend a lot of time in this lesson transitioning between this exponential form of an equation to this logarithmic form of an equation. Before we do that, let's graph both the original function and the inverse function. So the original function, remember, was 2 to the x. Let's just pick some x values and then calculate y values to get a good shape of the function 2 to the x. So I will just pick -2, -1, 0, 1, and 2. And then I'll calculate the y value given all those x's. So if I'm evaluating f at -2, I would do 2 to the -2. That's 1 over 2 to the +2, which is 1 over 4, which is 0.25. 2 to the -1 would be 1 over 2 to the +1, so 1 over 2 is 0.5. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. Notice these y values are doubling, and that's because the base of the power is 2. And I should remind you that exponential functions, they're going to have horizontal asymptotes at y equals 0, unless they've been shifted up or down by some c value at the end here, but we don't have one there, so it's at y equals 0. And now let's plot the points. And the function is going to look something like this. This is our original function, which was 2 to the x. And now if I want to graph the inverse, I don't have to choose points and do any more calculations. I know inverse functions just have their x and y coordinates swapped. So instead of having the point -2, 0.25, it's going to have the point 0.25, -2. And do the same for each of the remaining 4 coordinates, just swap their x and y's. So 0.5, -1, 1, 0, 2, 1, and 4, 2. And then I'll plot all of these points. And this function actually looks like this. Notice this function doesn't have a horizontal asymptote, it has a vertical asymptote at the line x equals 0. Remember, inverse functions, think inverse as opposite. So if the exponential function has a horizontal asymptote at y equals 0, the inverse function is going to have the opposite of that. It's going to have a vertical asymptote at x equals 0. And let's fill out a table of the properties for these. So for the 2 to the x function, the blue function, it doesn't have an x-intercept, but it has a y-intercept at the point 0, 1. For the inverse function, it doesn't have a y-intercept, it never crosses the y-axis, but it has an x-intercept at 1, 0. See how they're opposites of each other? The domain of the exponential function, the blue function, is xer. But the range, notice it's always above 0. So y can be any real number as long as y is above 0. The inverse function, remember inverse functions have their x's and y's swapped. So instead of having x any real number, the range is y can be any real number. And instead of the range having to be y greater than 0, the domain is x is greater than 0. Look at the red function, it only exists for x values bigger than 0. And like I was talking about asymptotes before, the exponential function has an asymptote at y equals 0. That means that the inverse, the logarithmic function, has a vertical asymptote at x equals 0. Okay, let's move on to more of the new stuff for this unit, where we're going to get some information down about properties of logarithmic functions. So a logarithmic function is the inverse of an exponential function. Okay, and then in this box here, let's look, it says if we have a logarithmic function defined like this, I would say y equals log base b of x. In that notation, y is the exponent that would go on the base b that would give me the value of x. That's what that means. So when you read this equation, make sure you understand y is the exponent that goes on b to get x. Or another way of saying that, b raised to the power of y equals x. So an equivalent way of writing this would be b to the power of y equals x. This function and this function mean the exact same thing. They're equivalent to each other. And I also put a note in the middle here explaining to you that the base of the log is always going to be a number bigger than 0 but not equal to 1. And once we start to understand log functions a little bit more, we can talk more about why that is. Down here it says, in other words, the solution to a logarithm is always and how I want you to think of it, I want you to think of the solution to a logarithm as an exponent. Because if we evaluate log base b of x, what we're evaluating is what exponent goes on b to get x. That's why we say the solution to a log is an exponent. That's why logarithmic functions are so useful for solving for unknown exponents. And I mentioned something called a common logarithm earlier. If we have a logarithm that's base 10, we call that a common logarithm, and that means we don't have to write the base. So if you see a log without a base, know that the base is actually 10. So for example, if you see log of 100 and you don't see a base on that, I can still evaluate this because I know the base, even though I don't see it, is actually 10, which means the answer to this logarithmic expression would be 2, because 2 is the exponent that goes on 10 to get 100, right? 10 squared equals 100. That's why the answer to that was 2. So let's spend the rest of the lesson working at transitioning between exponential equations and logarithmic equations. Let's start with this bottom one. If I give you a logarithmic equation, can you rewrite it in exponential form? And if you understand what a logarithm is, that's not hard to do. We know that evaluating this will give me the exponent that goes on b to get x. So this tells me that y is the exponent that goes on b to get x. So I could rewrite this as b to the y equals x. How about going the other way? What if we started with an exponential equation? Can you rewrite that in logarithmic form? Well, remember, the answer to a log is an exponent. So the exponent is the answer to the log. And remember, that's the exponent that goes on b to get y, which means the base of the log is b and the argument is y. X is the exponent that goes on b to get y. That's equivalent to what's written here. X is the exponent on b to get y. So let's work at moving between the two forms of an equation. These are all exponential equations. Let's rewrite all of them as logarithmic equations. So remember, the exponent is the answer to the log. So I'll write 4 equals log, and that's the exponent that goes on 2 to get 16. Another thing that would be helpful to notice that the base of the power becomes the base of the log, right? This logarithmic expression, if I were to evaluate it, it would tell me what exponent goes on 2 to get 16. And it'll give me 4, because 4 is the exponent that goes on 2 to get 16. So when we read this equation, it means that number raised to that number equals that number. And that's exactly where the equation came from. Let's try part B. The exponent is the answer to the log. since the base of the power was n, the base of the log is n, and the argument is m. This logarithmic equation means 3 is the exponent that goes on n to get m, and that's where it came from. Part C, the exponent is the answer to the logarithmic expression that has 3 as its base, since that was the base of the power, and 1/9 is the argument. So this means 3 to the power of -2 equals 1/9, and that's the exponential equation it came from. Let's go the other way. Let's write each logarithmic equation in an exponential form. So the answer to a log is the exponent that goes on the base to get the argument. So this means that 3 is the exponent that goes on 4 to get 64. Over here, remember this is the common logarithm. Since you don't see a base, know that the base is actually 10. So that means y is the exponent that goes on 10 to get x. Or another way of saying that, 10 to the y equals x. Now let's evaluate some logarithms. So I have a couple examples here. I'll do them each in different ways. So if I want to evaluate log base 3 of 81, so yes, you could just ask your calculator, what's log base 3 of 81? It'll tell you 4, but why is the answer 4? And how can we communicate that algebraically? Well, if I transition this logarithmic equation into an exponential equation, I would rewrite it as 3 to the power of y equals 81. So I'm really looking for, well, what exponent goes on 3 to get 81? That's what this means. So if I could rewrite 81 as a base 3 power, and I know 3 to the 4 is 81, I can now prove to you that y must be 4. Since the bases of these powers are the same, that must mean the exponents have to be equal. And that's what this rule here tells you. If we have two powers equal to each other, where the bases are the same, then the exponents would have to be equal to each other. The only way 3 to the y could equal 3 to the 4 is if y was 4. That's the only way the equation on this line would be true. Another way we could communicate our answer to a logarithm, we could rewrite the argument of the log as a power with the same base of the logarithm. So 64 is 4 cubed, right? So that's equivalent. And now if we look at what this says, if we're trying to evaluate this logarithm, we're trying to figure out what exponent could I put on that number to make it look like that. Well, obviously 3 would be the exponent that goes on 4 to make it look like 4 cubed. So the answer to this is 3. And let me just make this maybe a bit simpler for you. What does this mean? It means what exponent goes on 4 to get 64? That's 3. 4 cubed is 64. What exponent goes on 3 to get 81? That exponent is 4. 3 to the 4 is 81. And now let's do 2 more, but let's evaluate it however you want. Part C, this is a common logarithm. I don't see a base, so know that the base is 10. Now you don't have to write that in. I'm just showing that to you there. 1/100. Well, let me just start by rewriting that as 100 to the -1. And now 100 I could rewrite as 10 squared. So this would be equal to log of 10 squared to the -1. And then my exponent rule tells me I could multiply those exponents together. So this would be equal to 10 to the -2. So that tells me my answer to this is -2. Because since the base of the power in the argument and the base of the log are the same, the answer is just the exponent on the argument. And logically, this expression means what exponent goes on 10 to give me 10 to the -2. Well, of course, -2 is the exponent that goes on 10 to make it 10 to the -2. Part D, let's do it the other way. Let's rewrite an exponential form. So 2 to the power of y equals the argument, 1/8. And now I need to write that 1/8 as a base 2 power. So 2 to the y equals, well, 1/8 I could rewrite as 8 to the -1, and then 8 I could rewrite as 2 cubed, and then multiply those exponents together. I get 2 to the -3. Now, since I have power equals power, where the bases are equal to each other, I can just set the exponents equal. So y would have to be -3. Now, I realize, like I said before, you could just type either of those on your calculator. It'll give you the answer. Let me prove that to you. Log of 1/100 it'll give you -2. And log base 2 of 1/8, it'll give you -3. But my whole point of going through this with you is so that maybe you get a little bit comfortable transitioning between log and exponential equations. And you also hopefully get a better understanding of what logarithmic functions are. And you fully understand that the answer to the log, like in this example, -3, is the exponent that goes on the base of the log 2 to get the argument, right? 2 to the power of -3 is 1/8. And let me just change that to a fraction to show that to you. Okay, that's it for this lesson. I hope you feel comfortable, or at least more comfortable, with what a logarithmic function is. And in the next few lessons, we will learn some rules that we can use when working with logarithmic expressions.